Okay, so today we start to talk about algebraic graph theory. The idea to use linear algebra to understand graphs is very deep. It actually involves a lot of mathematics. So here, let's try to give a little taste of this idea. So in this first part, I will talk about adjacency matrix of a graph, say G. Okay, so I will give the definition and prove one theorem, and then in the second part we will see a little more algebra. So G is a graph. So for example, it has V and E, so it has a vertex set and edge set. And so suppose V of G, so let's say edge is n. The edge number is n, so it has a vertex number is n. It has exactly n vertices. Then we will define the so-called adjacency matrix, which depends on G of course, to be a n by n matrix. So definition is pretty simple. So if you write, so by definition, so if you write this as Aij, for example, Ij greater or equal than 1, smaller or equal than n, so this is a way to write a matrix. If you have this, then by definition here, Aij will equal to 1 if Ij is an edge. Okay, so it's this matrix is a 0, 1 matrix. It only have coefficients 0 or 1. And Aij is 0 if not, if Ij is not, is an edge. So here, look, so if we took Ai, clearly is not an edge. So this is always 0. Okay? So I mean, for any graph G, Aii, the diagonal entries, the diagonal elements, the diagonal coefficients, whatever name you wanted, have to be 0 for all position, because it never represents an edge, because we don't allow this graph to be to contain loops, so we don't allow edge to join the same vertex. So in other words, we talk about simple graphs. Okay, I think it's pretty clear, right? For example, let's see an example. For example, I can draw anything like 1, 2, 3. I just put numbers for the vertices, and maybe this is 4. Okay, so we got so this is my graph G. Then I will define A to be 4 times 4 by 4 matrix, and so it has 4 lines for rows. Okay, so this is kind of like a first row, second row, third row, and fourth row. And here have first line, first column, second column, third column, and fourth column. We have 16 positions. For example, A11 is here. It has to be 0. A12 is 1 because I have an edge here. You see, and you can look at the first row here. So it represents the vertex 1 will join which vertex. So you have 1, 2 and 1, 3, 2 edges. So you see this position should be 1, this should be 1, and this position is 0. Because 1, 4 is not an edge, is a non-edge. Okay? So similarly, how to fill the second. So let's first put all zeros here, because I know that A22, A33, A44 are all 0. What is A23? So 2, 3 is an edge, so we have 1 here. Okay? And what is A24? 0. What is A34? 1. One thing is interesting is that A12 and A21 are the same because they represent that 1, 2 is an edge or 2, 1 is an edge. They are the same thing. So this matrix is what we call symmetric matrix. So if you draw this axis, the whole matrix is you can reflect it and get the same thing. So what happens is like this: 0, 0, 0. Here is 1. Sorry. Okay. Here is 1. Okay. So that we got this. When I said that this matrix is symmetric, in the sense that A transpose equals A. Okay, do you know what is a transpose? So if we have Aij as the expression of A for every general position Ij is Aij, then A transpose will be Aj. It means that in the position Ij, I put A. In the position Ij position, I put Aj there. So it's exactly means that you make this reflection. Okay. So okay, this is the basic notation in matrix, and this is the definition of adjacency matrix. Okay. So here. So this is just a definition. I want to show a theorem. I prove a theorem, which tells you why this is efficient to represent a graph using matrices. But before that, let's recall something we already talked about. Recall walk on the graph G is just we put V1, E1. V2, E2, a sequence of vertices and edges alternatively. V3, E3, for example, and so on, and until Vk minus 1, Ek minus 1, Vk. Okay, so we have k minus 1 edges and probably k vertices, but they can be repeated. Okay, for example, I can put in our graph here 1, 2, 3, 4. I can put 1. For example, this is E1, E1, 2, E1. I can come back. Okay, E1, 1, E1, 2, whatever. Here we got E2, maybe E2, 3, E2, 3, and so on. So this is walk. So this is the walk. The general definition of walk is not a pass. Pass, really, we do not allow any repetitions. And walk, we can use edge repeatedly. Okay, so we are looking at walk. So this walk we usually call this is a walk with k edges. Okay, sometimes we call it has length k. But different authors have different notations to express length. So to be precise, I'll ask this path to have k edges. Okay. So because it has k edges and okay, with k minus 1 edges, in fact. Okay, so with k minus 1 edges, so okay, maybe k edges. Sorry, I put ek. I put something different. So I need k edges. If I put k edges, I have to vk, ek, vk plus 1. Okay, so we have k plus 1 vertices. So you see, this confusion come up very frequently because we have to be precise. Everyone knows precisely what we mean to have a length k. Okay, so at this point I will stress this path, this walk has exactly k edges. Okay, so furthermore, if v1 equals vk plus 1, so if the starting vertex and the ending vertex are the same, we say this walk is a closed walk. Okay, so we just we will do this. Okay, so we will show that matrix, adjacency matrix, will help you to count walks, which is really cool. So let me prove a theorem. So for any k, positive integer, let A be, for example, adjacency matrix for a graph G. Okay, so let's say n by n. Okay, so let's say n by n. So G has n vertices. We look at the matrix A to the power of k. So it's a product matrix of exactly k copies of A. Alright? So the entry of the coefficients, the entry ij, the position ij of A to the power of k. Sometimes we just put a k ij. Okay, we will write this below. Okay, so this guy, it is equal. This guy is a number. Okay, so remember A is a 0, 1 matrix, and we put A times A times A k times, which gives me A to the power of k. So it's another matrix. And I pick a position ij. I talk about the entry at this position for this matrix A to the power of k. So this entry is exactly what? Exactly what? The number of walks of length, okay, of edge length k, starting from the vertex I and ending at the vertex j. So we count the total number of walks starting from the vertex I and ending at the vertex j and of edge length k. Okay, we count how many walks in total are there satisfy these things. So you have to start from I and ending at j, and I have k edges. So this is exactly this number. So it's you just make multiplication for matrices. You get a matrix, and the matrix, all the coefficients mean something. I think this is very beautiful. Okay, so let me make a proof of this. This proof is nothing fancy. It's just definition of matrix multiplications, really. Okay, so let me do this carefully. So let us recall matrix multiplication. Okay, so for example, you put a squared, which gives you what? So you have aij, which is a n by n matrix, and aij again the same thing. which is a n by n matrix. So it's for example, Xij. It's another n by n matrix where you have Cij equals a sum of k products. So k from 1 to n, a ik times a kj. Okay. Okay. So similarly, let's recall what is ak, a to the power of k. It's something Cij again. For example, I put Dij maybe, Dij. So the result is an n by n matrix again. And what is Dij? It should be a sum of many things. So you have to put I1, I2, Ik minus 1. So you have to put it because a to the power of k, you actually make k minus 1 times of matrix product. Each time you have a new index, so you have k minus 1 indices. So this is like I start from I, okay, and I1, and then times I1, I2, times I2, I3, and so on, times Ik minus 1 j. Okay, you have to end ij. So I think this expression already gives you the sense that we are actually counting walks. Okay. Okay. So let me make some observation. So what is this number? Let's make some observation. First, if some element okay, so it's a sum of many terms. So if in one term, one ik one I1, I2, and Ik minus 1 were given, okay. For example, we look at one of the sums. If in one term, sum, for example, what do I mean by one term? I write it down. In one term, I1, I1, I2, and so on, Ik minus 1 j. Okay. In this term, if any one of the elements here in this product is 0, then this term is 0. I'm just saying that if one of them is 0, the product is 0. So in particular, it implies that this term is 0. So this term, let's write it another way, does not contribute to the final solve. Right? I think this is clear, right? So it got 0. And in another case, if all of these elements are 1, so because we are talking about 0, 1 matrix, every element is either 0 or 1. So if there are no 0, it means exactly all of them are 1. So if all of them are 1s, then what happens? Then it means that okay, so let me see. So it means that, so if you start from the vertex I1 is an edge, okay? So 1 means it's an edge. And maybe I write I1, I2 is an edge also. So note, the I2 could be I. Okay, so I use the symbols, it could be the same. But let's say, so I2 to I3 is also 1. All of them should be 1. So until Ik minus 1 to j, this is also an edge. So all of them are edges. Translate this. So this all elements are 1 means all these are edges. Okay, so in this case, it gives a walk from I to j with edge length k. Okay, so you have this, and at the same time, you have a walk here, and this at the same time, this term contributes 1 to the sum. Okay, so I think this is pretty clear now. So we have studied all the cases when the term contributes 1 to the sum. We are kind of counting 1 when we see exactly a walk from I to j with edge length k. So conclusion, this sum, which is just dij, okay? The sum, total sum gives you, by the formula, gives you dij, is, let's repeat this, the total number of walks from I to j of length, edge length k. Okay, so this is the proof. Okay, so this is the first part. Let's meet in the second part. I will continue to do some more linear algebra and its applications to graph theory. Okay, see you a bit later. So I'm going to continue talking about how we apply linear algebra to graph theory. So it's a very big topic. I'm only introducing some basic stuff. So first part of today, we talk about adjacency matrix. So in particular, we have shown that if we look at adjacency matrix A, then each entry of A to the power of k, this thing counts the number of walks from I to j of edge length k. Okay, so this is the theorem. So now we need to introduce recall a little more linear algebra. So let me remind you that we are dealing with a so-called symmetric matrix, because our adjacency matrix is a symmetric matrix. Okay, so if A is a real matrix, and so actually in this case, I don't know if you have taken a course in linear algebra. So it has exactly n real eigenvalues. Maybe we call lambda 1, lambda 2, and the lambda n. So here the lambda could repeat. Okay, so maybe we put a lambda equal 1, for example, for 3 times. So repeatedly. So probably with some repetitions. Right? And also we can find a so-called orthonormal basis using eigenvectors for these eigenvalues. So using corresponding eigenvectors. Right? For example, we put V1, V2 until Vn corresponding to these eigenvalues. Okay, and this basis are called orthonormal basis, meaning that we have the norm of each Vi is 1. And if we put Vi, Vj with different indices, then they are 0. So their inner product is 0. If I is not equal to j, then their inner product is 0. All right, these things, are you familiar with these things? I'm not going to use very complicated linear algebra, but this you have to know. So this is true specifically for symmetric spaces. Okay, if the symmetric matrices. So if you are not talking about symmetric matrix, it is possible that you have two eigenvalues complex. Okay, for example, usually so this thing can go to very, very deep, so it can be very complicated. But if you remember something and just try to use them and take it as a black box, is fine. Okay, and it's very important. For example, this is not true if we are doing something like, for example, 1 minus 1. This kind of not symmetric matrix. Usually, it has two eigenvalues, complex eigenvalues, conjugated. Right? So you are forced to go to complex vector spaces, which is complicated. It can be very complicated. But for now, we are not going that far. We are satisfied with this symmetric theory because our adjacency matrices are symmetric matrices. So say we have this A is n by n matrix. A is an n by n matrix. So if we have these eigenvectors, which we call v1, v2. Okay, we already have this. So we look at okay, with these objects, we know that A times Vi, for example, it equals lambda I Vi. So this is the definition of eigenvalue. Okay, so if you restrict on this vector and you look at the action of A on that vector, it has the effect of multiplication by a scalar lambda I. The scalar is what we call eigenvector, eigenvalue. Okay, so then we will write U, which is a matrix actually. So we write it as a column vectors. We write it as okay, maybe I put a V. V is a matrix. It is obtained by writing down these eigenvectors as columns. So see, so this is Vn. Okay, so for example, each V1, each Vi, it could be something like a Vi. I don't know. So maybe I should put a Vi1, Vi2. It's the coordinates of this Vi. So Vi1, Vi2. It's a little strange. My notation is a little strange. I just put an example for this. Okay. So this is and I write it down. This is a column vector. I put it here. So I got this. So V. So this is actually, if you expand all the column vectors, it's an n by n matrix. Okay. So this way, you find that what is A times V? The action of A on the matrix. This matrix multiplication, it gives you a V1, right? A V2 and a Vn. Okay. And then it is by definition, it is lambda 1 V1, lambda 2 V2 until lambda n Vn. You have this identity. And then actually it equals, you see, I put v1, v2 as this again, and I write this way. All right, so it's a diagonal matrix. All of diagonal entries are zeros. So you can verify the multiplication. So exactly this equals lambda 1 v1. You see, the first row times the first column, you get lambda 1 v1 and put it here. The second, you get lambda 2 v2. So, okay, so then, and this is v itself. So you move this to the other, to the left hand side, you get v inverse a v equals lambda 1, lambda 2 diagonal matrix. Okay, or probably it's equivalently a will be v times this diagonal matrix and v inverse. Okay, so we are saying that in this case a is conjugated is similar to a diagonal matrix. So the whole process is called diagonalization. Okay, this is the main part in linear algebra. Kind of if you can use a invertible matrix to change a matrix into a diagonal form, the matrix becomes easier, and essentially it does the same thing. So this v times something, v inverse times something, and times v, you understand this as a change of basis. All right. So this is the thing. In general, we know it's true in general. Now we want to relate this into a graph theory. So we got this theorem. So given a graph G, and let's put right its adjacency matrix. A, which is n by n symmetric real matrix. Actually, it's 0, 1 matrix. Okay, and it satisfies above. Okay, let's remember this. We will use this eventually. And then suppose lambda 1, lambda 2, lambda n are the eigenvalues for A. So actually, in this case, it's very standard to also call these numbers eigenvalues of the graph G. Okay, it's a little strange. So if you talk about eigenvalue of a graph G, actually you mean this. You first get an adjacency matrix of the graph, and then obtain the eigenvalues. And these eigenvalues you call eigenvalues of G. Okay, so so this theorem says that for all k positive for any indices, I'm interested again in this I. So ij. Okay, ij. Okay, right. So we know this from previous theorem. This is a constant, the number of walks. But now we want to use eigenvalues to write down what is this number, to give a formula. So this is actually a sum C1 of lambda 1 to the power of k plus C2 to the lambda 2 power of k, which is very interesting. So it's a weighted sum of all these eigenvalue powers, where it's we have to decide all these coefficients, where each CP, for example, P equals 1 to each guy is a sum VIT, VJT. Okay, so what is VIT? So here, remember here we have this
Okay. What I want to say is that I want to write this V to be, you see, V1, Vn as column vectors. I don't remember. I want to expand each Vi to be V11, V12, or V2, V11, V21. Let's see. Okay, it will be clear what this means. It means the i's vector t's coordinate. I think maybe all the opposite. Let's try to prove this. I mean, this each coefficient is decided by the vector I wrote here. Okay, the orthonormal vector corresponding to these eigenvalues. Okay, so it will be clear. So let's finish the proof, do the proof, and then come back to see what these things mean. To recall this, we know that V inverse of A to the power of K of V is what? This is lambda 1 to the power of K, lambda 2 to the power of K, and so on, lambda n to the power of K. Okay, this is because if we put 1 here, it will be diagonal matrix. And if you put K times V inverse of A, for example, V times V inverse A times V, you cancel this, and then you get V inverse A squared of V. Okay, so you put K times here is the same as V inverse A of V bracket to the power of K. Okay, so it's the same thing. So you have this computation. Okay, this is why diagonal matrices are good. So we have this, and then therefore, what is A to the power of K? Then it will be V times lambda 1 to the power of K, lambda 2 to the power of K, and the lambda n to the power of K. And here we get V inverse. Okay, so what is V? V, as we write it, it's a column vector V1, V2, Vn, right? And multiplicated by lambda 1k, lambda 2k, until lambda n to the power of k. And here, V inverse. So this orthonormal basis have the good thing that inverse is the same as its transpose. Okay, so we can write it V transpose, V2 transpose, until Vn transpose. We have this. So if we expand this, we will find I think it will be something like let's write V1 to be V11, V21 until Vn1. Okay, as this first vector. So this is a V11, V21 until Vn1, and this guy is a V12, V22 until Vn2. And here you have V1n, V2n until Vnn. And then we have this diagonal matrix and lambda n to the power of k. And you have here, you have V11, V21, Vn1, and so on. Here you have V1n. So it's a transpose of this matrix. So, and Vnn. Okay. So what is this? What is this? So to understand this matrix, so this is A to the power of k. This is A to the power of k. So in particular, this will obtain an n by n matrix, and A to the k, the position ij will be what? So we have to use definition of matrix multiplication. Okay, so it will be so what is A, for example, times B, the position ij will be a sum k such that aik and bkj. Okay, if you go to the product of three matrices like this, it should be a sum of three. It will be a sum of three indices, many terms, but many terms are zero. Okay, so let's see. So how to do this? So I think it's a let me see. So for example, if you multiply this with this, you get only lambda 1 1 v1 lambda 1k, the first coordinate, and then okay, so you have v2 lambda 1k like this. We n1 lambda 1k. Okay, and so basically every row here will multiply. Sorry, I mean every column here will be multiplied by lambda 1 to the power k. Second column will be multiplied by lambda 2 power k. Okay, so we have v1 2 lambda 2 to the power k, v2 2 lambda 2 power of k, and vn2 lambda 2 to the power of k. Okay, so in the end we have v1n lambda n to the power of k. I don't know, maybe if you use sum symbol, make it simpler, but to be careful, let's do this in a very complicated way, but more elementary. So we have this and vn1. So this is again ak. Okay, it's again ak, and v1 and v2 and until vn, something like this. And then, for example, I'm looking at a to the power of k ij. It will be so I think probably I need to put it 1 1 again. So it will be this line, this row multiply this. So it will be a sum v1 lambda 1 to the power of k v1, and here plus v1 2 lambda 2 to the power of k v1 and v1 2. Okay, right, and plus the 1 n lambda n to the power of k v1. Okay, so if you believe me, eventually we can prove that for any ij, a to the power of k ij will be a sum p from 1 to n. Here you get lambda p to the power of k, and here you have pi vip and vjp. Okay, so here it's not very clear. Right? This is v1n and this is v1n also, but this one actually corresponding to this, and this one corresponding to this. You can check this. So a to the power of k ij will be this sum, and it will be just this is what we want to prove. Do forget what we want to prove. This is the sum we want to prove. It just each cp will. It implies that each cp will be VIP times VJP. All right. All right. It's a little complicated. If you I mean, if you are very familiar with this kind of computation, for example, if you are doing a linear algebra course right now, it should be fine. But if you haven't done this for a while, it's a little or bit overwhelming. So I think if you write down notation using some notations, it could be more complicated, but it's fine. Okay. So an interesting particular case. So let me make a comment. an interesting particular case. So let's recall the statement of the theorem. Okay, so if I ask for AKII, so I look at the closed. Look, I look at the closed box. Okay, is AKII, for example, diagonal entries in the final matrix. So by the previous theorem, first theorem in the recording, so we know that it is which is the total number of what we call closed walks from I to I. But starting from I ending at I of edge length K. Okay, so it has a meaning. It counts closed walks. And by this result, so you see AKII is what? By the second theorem, the theorem I just showed, it is P from 1 to N VIP squared, because I equals J here, times lambda P to the power of K. Okay? So what I'm talking about here, I think is some problem. Okay, I think I did something stupid, but let me see. Yeah, I think I did something stupid. I'm sorry. I think I want to keep this notation of not to expand it, making it more complicated and wrong. I want to keep this notation as this vectors. Okay, so it is simple actually and correct. Sorry for this part, but what I want to do is that I keep this notation. It becomes easier. So I made some mistake. So then I think it's clear that I keep this notation. It becomes very clear here. You have V1 lambda 1 to the power of K times V1 transpose. Okay, so this is not a number, but it's this is not a number. Okay, this is not a number, but it's a vector, and plus V2 lambda, you see, V2 times lambda 2 to the power of K V2 inverse here. I think it's better I write big V as vectors. And plus, and here we have Vn, big V. So lambda n to the power of K Vn transpose. Okay? So let me forget about this. It's a little annoying. Sorry. And then what is that? So then I got a sum, which P from 1 to N. Okay, so each we get V. What? Yeah, I think it's correct. So we got lambda P to the power of K. We have lambda P. What? Is it correct? Sorry, I think something is off here. So first thing, you have V1 and lambda 1 to the power of k. So this is a number, and we okay. Okay, it's completely wrong. Okay, so this is completely wrong. So let me so this is a 1 by n matrix. Okay, sort of. This is n by n matrix. What I get is a 1 by, so we have V1 times lambda 1 to the power of k, and right, 0 0, and the second column will be V2 lambda 2. Yeah, it's correct. And then Vn times lambda n to the k. Okay, it's correct. And then V1 transpose Vn transpose. Okay, so then we got yeah, V1, but V1 is a vector. V1 lambda 1 to the power of k. V1 inverse. Yeah, right. Plus V2 lambda 2 power to the k V2 transpose plus Vn lambda n to the power of k Vn transpose. Right. Sorry. And what I want to do about this? So then I have, it should be a sum, right? A sum p. So you get Vp transpose times lambda p to the power of k. Is that so? Yeah, right. Okay, so first maybe my first version is not wrong, but I got confused. So I hope this time we got correct. So if we write Vp as V1p, V2p, for example, Vp until Vnp. Okay, so this matrix will be V1p. This, because Vp is a column vector, so we got V1p, V2p, and Vnp as a, so this is Vp times Vp transpose, Vp times Vp transpose. So this equals V1p squared, right? V2p, V1p answer. And Vnp, V1p. Okay, this is the first column. So we just multiply this here. So and the second column will be, you multiply it here. You multiply this number here. So you have V1p, V2p, and V2p squared. And here you have Vnp, V2p. And here you have V1p, Vnp. And you have Vnp squared, something like this. Okay, this is a matrix in each term here. So if you take a to the power of k ij, you have to take ij here for each p, and this is correct, I think. So eventually this but this should be a sum. Okay, so for all p here, cp should be, let me something is wrong. Okay. Okay, it's okay. It's okay. Each CP is a number like this. Each CP is a number like this. But okay, what's the problem? So why I feel a little wrong here? So I'm looking at a to the power of k I, and if it gives me this, right, it's okay. I see. So I count. Sorry. Okay, I know what's going on. I count. This is actually right. So this AKII, it must be by this. This AKII. It will be what? I think it's correct. So let me P equals from N, from from 1 to N, you have VIP squared lambda P to the power of K. Okay, I see. So now, so it's not very clean at this point, but I count all the, okay, I know what's going on. All the closed walks of edge length K. So it means that I need to make a further sum. So I need I from 1 to N. I start from vertex 1 and end at vertex 1. And I start with vertex 2 and at vertex 2. Okay. I make all the sums of AK of II. So actually this is diagonal, the sum of all the diagonal entries. It usually is called the trace of the matrix A to the power of K. So this, so then I have I to the from 1 to N, P from 1 to N. You have this VIP squared lambda P to the power of K. So somehow I change the order of these two sums. So it equals P from 1 to N. I get this. I from 1 to N. VIP squared. This, okay, lambda P to the power of K. This gives you 1, actually, okay, because you are an orthonormal matrix. Each vector, so we are looking at a column vector, so which is V1P, V2P, and VNP. This square sum of this column vector equals 1. So it gives you P to the 1 to the N, from 1 to the N, lambda P K squared. Okay, this is the conclusion. So sorry for the confusion. To sum up, so the trace of A to the power of K, which counts the total number of walks, closed walks, of edge length K, this thing is equal to the sum of all the eigenvalues to the power of K. I think this is a pretty cool assumption. So these eigenvalues, you don't even know, I'm not sure, you don't even know they are integers. I'm not sure, is this correct or not? Is it possible some of the eigenvalues are not integers? But if you take the powered sum of them, it counts something. Clearly, it has to be an integer. Okay, so let me let me give a final example to okay, so the example, I'm not giving all the details. You can read my notes later. So Kn, the complete graph. So you can track using a linear algebra. So first of all, what is the adjacency matrix for Kn? It's very, very simple. You have a 0 here because you don't have edge for example, between any vertex to itself, but you have 1 for all other. So let's write K4, for example. Let's say 0, 0, 0, and then all other entries are 1s. Okay, so this is adjacency matrix for complete graph K4. Okay, so what happens is that you can check its exercise. You can check that it has 2 eigenvalues. One eigenvalue is -1, and with multiplicity n-1. So we have eigenvalue here and the multiplicity n-1. So it means that okay, you have lambda 1 equals lambda 2 equals until lambda n-1. Every one is -1. There are n-1 copies. So there are multiplicity of the eigenvalue -1 is n-1. And there is another one eigenvalue n-1, which has multiplicity 1. So you have the final eigenvalue is n-1. Okay, so it's not very hard to see. But for example, if you look at the all 1 vector, 1, 1, 1, 1, 1. So what is a times 1, 1, 1, 1? So it's you see 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0 times 1, 1, 1, 1. Okay, so I think it's very clear. It's equals 3, 3, 3, 3. Because you are summing this to 3, 1, 1, 1, 1. You are summing every row to 3. So it in particular it equals 3 times 1, 1, 1, 1. So this vector is an eigenvector and 3 is your eigenvalue. In the general case, it's n-1. The eigenvalue is n-1. Eigenvector is all 1 vector of length n. Okay, so this is an exercise in linear algebra. And after this, we can compute. We can, for example, count what is the total number of closed walk of length k. So what is AK? Trace of AK. So it's just a sum of all these eigen value to power of k. Okay, so okay, so I think you have n -1 to the power of k, right? Because you have 1 eigenvalue n-1 plus -1 this eigenvalue to the power of k, but you have n-1 copies of them. So this is your result. And if you think about it, for a complete graph, for example, you have v1, v2, and vn. So every vertex is basically the same, right? So you can think you can if I ask you the total number of closed walks from v1 to v1, I think it's easy to imagine that it is the same with the total number of walks from v2 to v2, because they are two any two vertices in a complete graph are similar, right? I mean, there's some kind of high level symmetry between them. So it implies that the total number of closed walks from V1 to V1, okay, is what? Is 1 over n times this number. So have this number, n minus 1 to the power of k. Okay, I think it's a very nice application. You can do this for many familiar matrices, for example, complete bipartite graph, and many more. So as long as you can compute their all the eigenvalues and their multiplicities. Okay, everyone happy? So I think this concludes the class for today. Okay, so any questions? Okay, great. So I think there is some complication. I made some mistakes in the computations, but really it comes the unfamiliar computation from linear algebra. If you accept, yeah, I mean, if you accept a linear algebra, and short of the real part I want to show you is how to use matrix multiplication to manipulate counting. So it's a very beautiful stuff. But my presentation I did as best I can. So I hope you can check my notes. I try to write it cleaner. So okay, so okay, let me finish the recording.